Alright, in this video, I'll be doing LeetCode Weekly Contest 200 and explaining, hopefully, the solutions to all 4 problems. If this is a especially hard contest, then maybe I'll be only able to do 3, but yeah, wish me luck. So that was a great contest. It was Weekly Contest 200. You only get that once every 100 contests, and this is the second 100th contest. So pretty special contest, but considering that I didn't do very well, I guess I got 700th place. I mean, that's pretty good, but usually I would expect higher. Maybe this was a harder contest for me, at least. I think it was a harder contest in general as well, because the problems were more likely to have mistakes made on them, and they were just harder problems in general. So I'm going to be explaining the solutions now. Problem 1, count good triplets. Given an array of integers r and 3 integers a, b, and c, you need to find the number of good triplets. A triplet is good if the following conditions are true, and then it lists the 4 conditions. Return the number of good triplets. So we're asked to find all triplets that satisfy these 3 conditions. I should make this bigger. And to do that, we notice that the array length is only going to be a 100 at most. So we can actually just bash through all triplets. And this is going to take n cubed time, but since n is 100, that's totally doable. And then we just check all 3 conditions, and if so, then we add 1 to the total. And then we just return the total. So yeah, pretty simple problem. This is brute force. Problem 2, find the winner of an array game. Given an integer r of distinct integers and an integer k, a game will be played between the first 2 elements of the array. In each round of the game, we compare r0 with r1, and the larger integer wins and remains at position 0, and the smaller integer moves to the end of the array. The game ends when an integer wins k consecutive rounds. Return the integer which will win the game. It is guaranteed that there will be a winner of the game. Okay, so at first I implemented a pretty dumb segment tree solution, but it actually got accepted, and it was the first one I tried. But segment tree is way too overpowered. There is a much better way to do this. So I'm going to explain it here. So first thing to note is that if k is greater than the length of the array, then we don't need to consider any values greater than it, because if k is greater than the length of the array, then all of the numbers are just going to loop around, right? The winner is just going to keep winning if they've won the first n games already. So once we know that, we can just make k the minimum between itself and n to make sure that we don't go beyond the length of the array. And then we need to make sure that an integer wins k rounds. And how does it win k rounds? Well, we know that every integer is going to come to the front of the array eventually, because all of the numbers in front of it are going to lose at least once. And this means that we just need to make sure an integer is going to be greater than the first k numbers in front of it. And how do we do that? Well, we keep a count of the number of wins the current winner has won so far. And we keep track of the current winner by a variable called cur. And this is going to track the index of the number that we're looking at. And if at any point the number of wins that this integer has is greater than or equal to k, then we can just return it. But how do we keep track of wins? Well, we just loop through the array once, and if at any point a number is greater than the current winner, then we need to reset that. We need to reset the winner to the current one, and then we need to set wins to 1, because we know it's going to win against our previous winner. And then if this current number is less than the winner, then we know that we can add 1 to the number of wins, because our current winner is going to win against this current integer. And if they're the same, this is just an edge case. It's going to happen if the current winner is the current number we're looking at. At the end, if we haven't determined a winner, then we know the maximum value of the array is going to win. And we know this because each number is distinct. So the maximum number is going to come to the front eventually, and then just beat numbers forever, because every other number is less than it by definition. And yeah, if we find a winner during our loop, return it, otherwise return the max. So this is a much simpler algorithm than my segment tree algorithm, which we can find over here. Yeah, segment tree stuff, and then some stuff over here. You can read it if you want. It's a more complicated algorithm, I guess, but but it made more intuitive sense to me, at least. Problem 3. Minimum swaps to arrange a binary grid. Given an n by n binary grid, in one step you can choose 2 adjacent rows of the grid and swap them. A grid is said to be valid if all the cells above the main diagonal are zeros. Return the minimum number of steps needed to make the grid valid, or -1 if the grid cannot be valid. The main diagonal goes from 1, 1 to nn. Okay, so what we do here is a greedy algorithm, and I'm going to draw an example. So, our example is, what was the example? Let's see. 0, 0, 1, 1, 1, 0, and 1, 0, 0. Okay, so we need all elements above the main diagonal to be zeros. And this means that every row that's above the main diagonal is going to need to have all zeros at the end. So the ending position is going to look something like this, right? So there's going to be zeros here and zeros here. And this means all the rows that we're going to use above the main diagonal have to end in zeros. So we track how many zeros at the end of every row. So this one has 2 zeros at the end, this one has 1, and this one has 0. So we want the 2 to come over here because we need... So we want the 2 to come to the top row because the top row needs 2 zeros. We want the 1 to just stay where it is, and then we want the 0 to come to the bottom. And, well, how do we do this? How do we count the number of swaps that we need to make? Well, we start at the top row. Actually, right now, we don't actually need the matrix anymore. We just need a column which tracks how many zeros are in each row, because that's the only thing that matters. So 0, 1, 2. Right now it's 0, 1, 2. We want the 2 to come to the top. So when we're at I equals 0, we're looking at the 0th row. We want the row with 2 zeros to come to the top, and that means we're going to have to do 2 swaps because it's between indexes 0 and 2, and 2 minus 0 is 2. So by moving 2 to the top, we push all the other ones to the bottom. So we also need to do that. So 0, 1 gets shifted down. This part gets shifted down, and 2 comes to the top. After that, we set I equals 1. Now we're looking at the first row. We need this to have 1, 0. So we're going to need to swap these. And actually, the way we do it is actually we're thinking about it as we need to bring the 1 up. And that's going to push the 0 down. So that's going to make it 2, 1, 0. And then we're done. That's all we need to do. Once we got to the bottom row without any errors, then we can safely assume that we have altered the array so that all elements above the main diagonal are zeros. If at any point we can't do this, like we look at this 2 and we say, oh, well, there's no 1. So for example, if we have something like this, if it starts out as like 4, 0, 5, 0, 0, 0, well, okay, so what we're going to do here is we're going to bring 5 to the top. We're going to bring 5 to the top, but then we don't have, once we bring to the 5 to the top, we're going to bring the 4 here. But then once we're at this index, we don't have any 3s left. And that means we're going to have to return -1 because we can't make a row with 3 zeros. If at any point we can't do what we want, then we return -1. Also, when we're searching through the rest of the array to find the number of zeros that we need, we're going to look at the first possible one because that requires the least number of swaps. And it says we need to find the minimum number of swaps. So, yeah, we're greedy here. Yeah, I think this is a pretty simple problem, I guess. You just need to find the number of zeros in each row and then do a greedy algorithm. Yeah, I don't think there's anything I forgot. Basically, we reduce this to a 2D array of how many zeros at the end of each row, and then we do the swaps on those using greedy. So, pretty simple problem. Problem 3. Get the maximum score. You are given 2 sorted arrays of distinct integers nums1 and nums2. A valid path is defined as follows. Choose array nums1 or nums2 to traverse. Traverse the current array from left to right. If you are reading any value that is present in nums1 and nums2, you are allowed to change your path to the other array. Score is defined as the sum of unique values in a valid path. Return the maximum score you can obtain of all possible valid paths. And then we need to return it a mod 10 to the 9 plus 7. So this problem is pretty obviously dynamic programming. I mean, it's not that, it might not be that immediately obvious, but this is dynamic programming. It's just a little bit modified because we have 2 paths and each path can move to the other one. I think the best way to explain a dynamic programming problem is actually probably to do an example. So we're going to use the first example here. Okay, so the example is 2, 4, 5, 8, 10. And the second one is 4, 6, 8, 9. Okay, I'm going to write the DP array values above each of these. Okay, so the way I implemented it was actually top-down, which is just smart recursion. But the way I'm going to explain it here is bottom-up. It's basically the same thing, but explaining recursion is much harder than just doing bottom-up. So, okay, so we're looking at the end elements first, I guess. And it's at the top of the stack of the recursion. So DP value for this is 10 because we can only do 10. Oh, also, yeah, these arrays are going to count the maximum score we can reach if we start at the array element described. So 10 is the last element. We can't go anywhere, so it's just 10. 8, on the other hand, 8 can either go to 10 or it can jump to this 8 and then do something with this 8. So we need to find the DP value of this 8. Or we can just go to the 10. So we know this is going to be max 18 and some other number. And this other number is the DP value of this 8. Notice that we don't add the value of this 8 onto the score of the DP value of this 8 because it says here only one repeated value is considered in the valid path. So we're not going to count these 8s twice. We're only going to count them once. Then we need to know the DP value of this 8. And we're going to find that using recursion. But here I'm going to do bottom up, so we'll just do this 9 first. This 9 is only going to be 9 because again, it can't move anywhere. And then we can find the value of this 8. This 8 is going to look at this 8 because, actually, first it's not going to look at that 8 because the DP value for this 8 hasn't been computed yet. It's just going to look at the 9. So once it's looked at the 9, it's going to be 17. Max 17 and something else. Right, so something else. Okay, so then we go back to this 8 over here. We look at the DP value of the other 8. It's 17. It's going to be the maximum value of 18 and 17. So the DP value is going to be 18 for this 8. And then it sends that back to this 8 over here. And this 8 says, okay, well, the DP value of this is 18. Is 18 bigger than 17? Yes. So we're going to take 18. And the DP value of this 8 is 18. Okay. Next, we move back to the 5. 5 can only move to 8, so it's going to be 5 plus 18, which is 23. We look at this 6. It's going to be 24, since it can only move to that 8. Okay, then we look at the 4s. This is going to be the same situations as the 8s. We're going to have to do like two different steps of passing back and forth. So this 4 first says, okay, it's going to be the max of 23. And, actually it's going to be 27 because we're going to add this 4 and this 23. It's going to be the max of 27 and whatever this 4 has to offer. So it says that. It sends 27 to this 4 over here. This 4 says, okay, it's going to be the max of 27 and 28 because this 4 can add on to this 24. So the max value for this DP is going to be 28. So we know the DP value of this 4 over here is going to be 28. It sends that back to this 4. It's going to be the maximum of 27 and 28, so it's going to be 28. Okay, and then this 2 can only move to this 4. It becomes 30. And then all we need to do is just find the maximum DP value of the starting nodes. We can either start at this 2 over here or this 4 over here. This 2 has a larger DP value. It has 30. This one has a score of 28, so we're going to take this 30, and that's going to be our answer. Hopefully that was a good DP explanation. This is all the complicated code to make it. See here we use a recursion function. This is the base case if it's at the end. But also notice that if we're at the end, we could potentially jump to the other array. And that's why I got my first bug on problem 4. So we have to consider that I can go to the other array. Otherwise, it's just going to be the value itself. Okay, and then over here we find the index of the number in the other array. We can do this with a binary search because these arrays are sorted. And if they weren't sorted, it would be a lot more complicated because then we'd have to do some pre-processing, and I don't know if that's going to work. Since n is 10 to the 5, it has to be linear. And log n binary searching, easy. That just adds on a small coefficient. And then over here, we have to pass our DP value to the other value in the other array. Yeah, and then at the end, we just call it on the first ones, and then we return it. Oh yeah, of course we have to do the mod. I caught that in my first bug. And we can see here, this is a recursion function with caching, so this is top down. Okay, that's explanations of all 4 problems. Yeah, special contest. I did 700th place. It's not too bad, but worse than my average maybe? I don't know. So yeah, thanks for watching, and I'll see you next time. Bye.